Okay, hi everyone. I'm Michael Goin. I'm an engineering lead at NeuralMagic, recently acquired by Red Hat, but that's not important. We're still doing the same open source work. I'm a maintainer on the vLLM project. And thanks to Charles, you'll understand a bit more of this presentation as I blast you through a lot of the inference and model optimizations that you should be considering once you start deploying LLMs at scale. So first, just about NeuralMagic, we believe the future of AI is open. We're truly on a mission to bring more open source LLMs and the power of vLLM to more people through open source. That's the quick spiel. If you don't know what vLLM is, it's basically the standard in open source model serving. It's a fast, easy to use open source inference server for hosting language models of various types. The reason why people love it is that it supports all the key models. We actually work closely with the Hugging Face team, and there's now going to be a Transformers backend where you can run pretty much any model from Transformers, even when we don't have specific optimizations for it. It hosts a large variety of inference optimizations because it's sort of a platform and a base fork for a lot of research that gets folded into the project over time. And of course, it gets great performance on NVIDIA GPUs, but because of its flexible architecture in Python and PyTorch, while still being very performant, it can easily support other hardware backends like AMD GPUs, Google TPUs, AWS Inferentia, Intel GPUs and Gaudi and CPUs. And like I mentioned, it has a lot of inference features. It doesn't just support text large language models. It has multimodal support, embeddings, reward modeling, classification, scoring, re-ranking. There's many quantization styles, which I'll cover a bit here, and inference optimizations that I'll also cover. And of course, many features that are useful for building applications, like you get from the closed source APIs, like tool and function calling and structured outputs, thanks to outlines. And of course, parallelism, tensor parallelism, pipeline parallelism, and more to come, so that you can run models across multiple GPUs within nodes or in between nodes. And vLLM, as I mentioned, has some pretty easy to use interfaces. You use it by pip installing it or using the Docker images. It gives you a Python offline batching interface and an OpenAI compatible server that can get you started and moved away from the closed source APIs and start experimenting with hosting your own large language models. So some of the optimizations we'll cover today are model optimizations, which are where we're going to cover how to make the model forward pass fast. Each one of those tokens or prefills we generate, like Charles covered. And some maybe the more interesting things, and where a lot of research is, are systems optimization. So making everything around the model forward pass fast or more efficient. So such that with each model forward pass, you're getting more work done and you're keeping your GPUs more towards that 100% utilization that you're chasing. So first, model optimizations. First, I'll cover numerics. So as you probably kind of know, LLMs are a series of matrix multiplications with parameters. Each parameter ends up being a value represented by some number of bits. Usually, around 16 bits is what we tend to use for brain float 16 or floating point 16. And those bits are generally, used for two things, representing the sort of dynamic range. What are the maximum or minimum representable values in magnitude, and precision. How close can we walk around 0 to talk about 0.1 or 0.1.1, and those things. And why we talk about quantization, quantization is really a thing with the goal of reducing the amount of bits we need so we can get more efficiency, take up less space in memory, or potentially use more efficient compute units. And you can apply this on the weights and activations. Mostly, for this consideration, we're just going to consider the layers where we have all the parameters. Generally, we talk about them as the linear layers in the models. So first, there's weight-only quantization, which Charles already covered, where we're just going to quantize the weights and leave the activations at their original precision. The main purpose of this is reducing the memory requirements, so you can fit your model onto the GPUs that you have available. And it also allows you to reduce some data movement at the expense for a little bit of extra compute that you use to upconvert the weights for each forward pass. As Charles also rightfully mentioned, you can overlap these things due to the many compute units available in GPUs. And the CUDA cores we have to do some lightweight math are different than the tensor cores that we use to do the really big matrix multiplications. And this is probably the quantization that if you're in the open source community: GPTQ, AWQ, bits and bytes, GGUF. And these are the things that make the most sense when you're starting on consumer GPUs or trying to get an LLM fitting on your laptop, and you're just a single user doing batch size 1 decode inference. Now, another part of quantization is activation quantization. So this is where we're quantizing both the weights and activations. And this is really important because weight-only quantization is not really sufficient once you get to a certain amount of load, which you are when you're serving LLMs and trying to make money. So by quantizing the weights and activations, we can finally use those low-precision tensor cores that are on these data sheets every time a new GPU comes out and says FP8. You can't use those unless you quantize the weights and the activations. So again, to kind of cover why would you want to quantize the weights and the activations? So I was really happy when Charles mentioned arithmetic intensity, because here I have a roofline plot. Don't let it scare you too much, but really it's just about talking about on the left side of the roofline plot, we have memory bandwidth limited regime where we can't, where we're just don't have enough arithmetic intensity, we don't have enough compute. So we're limited by the bandwidth we have from the GPU. In terms of saturating all of the flops that GPU has. And you're there when you're in low batch decode, and this is where memory compression really wins. However, once you get to the right side with a bit more compute intensity, where you have large batches of requests that you're processing in parallel, or doing really long prefills for long context lengths, this is where you get into the compute regime, and we can actually use all the flops that are on the GPU. And this is where activation quantization is useful. And so I have a bit of a simpler graph, still complex, on the right side that has the gray line as an unquantized model, the yellow line as a 4-bit weight quantized model, and the blue line as an 8-bit weight and activation quantized model. And the y-axis is time per output token. So basically, how fast are you getting your streaming tokens? And the x-axis is the queries per second, or how many requests we're putting the server under load. And basically, you can see the weight-only quantization is fastest, actually, at 1 query per second. So it can be faster when you're in a memory-bound situation. However, as you start scaling your queries out, it's clear that having the weight and activation quantization gets you better results. And the other thing here is we have a time to first token of 5 seconds as our latency SLA. And this is why those other lines stop before the activation quantization line keeps going, because we can serve that latency SLA under more load, making more money. So another type of model optimization is 2-4 structured sparsity. This is NVIDIA's biggest marketing tool. It doubles all of their flops numbers. It's not as easy to get as quantization, but we work on it as well at Neural Magic. And this just offers you a straight doubling of the flops you have available and about a 40% memory savings if 2 out of every 4 parameters you have in your weights are 0. Basically, combining this with activation quantization is the way that you get to the peak flops that are available on your H100s. On the right here, we have another chart where the black line is a dense unquantized llama. Then the yellow is an FP8 activation quantized llama. And the green is FP8 quantization with 2-4 sparsity. And here, we just see it's a benefit for your time per output token all the way, because we have better compute available, and we have lower memory bandwidth requirements. One of the ways we make this really easy for you is we make optimized models all the time in open source. So if you want to play around with these different formats, all these different formats, go to our Hugging Face repository, where we'll have lots of models and evaluations, so you can make informed decisions about the accuracy of these different quantization methods, and also get them to run across various different hardware platforms by deploying them on vLLM. But you don't just need to get it from us. We also help make the LLM compressor project under the vLLM project. And this is a unified framework for applying quantization, sparsity, distillation algorithms to your models that you have just within the Hugging Face ecosystem. So give it a try. So next, I'll cover some system optimizations for LLM inference, aka all the things around the model. So one of the key things you want to think about here is chunked prefill. This is essentially trying to deal with the problem that your prefills and your decodes are so fundamentally different. If you look at the chart on the left, we have basically trying to show the amount of tokens you can get out of a model when you're processing prefills at different increasing batch sizes. You can see the prefill graph doesn't really change the amount of tokens you can get out of the model. So you're already pretty saturated. However, with decodes, you get astronomically more tokens out of the model as you increase the batch size of decode requests that you have. However, it's still not anywhere near close to how many tokens per second you're getting from a single prefill. So chunked prefill breaks down a single prefill operation into smaller chunks, so you can start to schedule those chunks of your prefill alongside your decode batches, so you can just get more compute utilization out of the GPU, aka just more tokens per second out of the GPU. Now, this is really cool for utilization and things like that, but this also has a benefit on actual performance and latency for the service that you're trying to provide. There's this kind of famous paper at this point that covers this idea of, instead of throughput, good put. We only want throughput when it meets our latency SLAs and when it doesn't feel bad for our users. So in the case of scheduling new prefills for new requests without chunked prefill, when we need to schedule a new prefill, the current decodes that we have undergo a delay while we're doing that prefill. And as a result, the user is going to see weird, uneven pauses between the tokens that they're getting. And their whole request is just going to take more end-to-end time. However, like with chunk prefill, we make that prefill take a little bit longer with a little bit of inefficiency by splitting it into chunks. But we get to keep that consistent time between decodes and overall get all the requests done faster. So it's really an important optimization that's enabled by default in vLLM. Another thing I want to cover is automatic prefix caching. So first, I'll talk about the reasons why this is useful. So you're probably familiar with ChatGPT at this point. Many of these models and open source models in production as well have system prompts that help guide them and prime them for being good assistants for you. And each time you send a request to these models, they insert a very large system prompt before your request. And these are identical between each of the requests on the model. Another example is multi-turn conversations, which obviously you run into when you're having a long-winded chat about something with ChatGPT. Once the LLM has responded to you and you want to ask another question or ask for further detail on that, trivially you're sending back all the data you've already talked about and now your new data, since the LLM has already both pre-filled your response and decoded its response to you, it should just be able to take that previous conversation from cache and not need to recompute it. So this is really important as you start getting to scale and not wasting pre-fills. As we know, they can be pretty expensive. So automatic prefix caching is pretty natural inside of vLLM because of the fundamental algorithm of how it implements attention with page detention, where we don't need contiguous key and value stores for keeping the cache of previous conversations. We can treat the KV cache like operating system virtual memory, and which is really useful for allowing us to pre-allocate all of our memory ahead of time and dynamically allocate more blocks for more requests coming in. And to add prefix caching, all you need to do is add a hash to each KV block, and now as you have your prompts coming in, you check your hash on that, and if you have something that matches in all of your KV blocks that you have, you just pull that in, and you don't need to prefill all those tokens. So another optimization is speculative decoding. This one is particularly useful for reducing the latency of generation. So taking advantage of another time where during generation we're generally memory bound. And also there's some tokens that are easier to generate than others. Think about cases where you're doing coding, or you're doing summarization, or really just repetitive tasks. We can generally use small language models that are aligned with the large language models in order to generate many more easy tokens and speculate on what multiple token outputs could be, and simply just run those through the larger language model in order to validate if those tokens were right. And then we just take the tokens that were right, discard the ones that were extra, and it's not that much of a penalty because we have the compute available. The great thing about this is that it's lossless because we always validate the tokens that we generate. So here I'll describe how you speculate with a draft model, as you kind of saw before. Usually you take a model within an existing model family. So if you're running Llama 70B, grab the Llama 1B or 3B. These are good model pairs just in terms of instruct models, but also if you have custom fine-tuned data or custom data sets, generally if you fine-tune a large model and fine-tune a small model, you can get pretty good alignment. The challenge is, if you don't have a draft model, if you're doing a custom model, how do you find that draft model? So it does take some work in order to find a model or create a model if you don't have it available. And I can talk about the performance benefits a bit here. You can see it gives pretty decent speedups at low queries per second, low requests, where we have that extra compute. But as you scale up the QPS to 8 at the end there, you can see it's not really giving any benefit. And actually, if we expand this chart far out to 16 or 32, speculative decoding can actually cause performance issues if you're still running it when you have a large batch, because it is adding more compute. So it's important that you have sort of dynamic methods for changing how many target tokens you're going to produce for a given request based on your current load. Another method that doesn't actually require a model at all is matching n-grams in the prompt, or otherwise known as prompt lookup decoding. So this is particularly useful in methods like summarization or coding, where effectively you expect the tokens that you're going to generate exist somewhere in your prompt, and just based on trying to match n-grams with what's been produced so far, you can produce all of these candidate speculative tokens as n-grams in your prompt, or from n-grams in your prompt, and just run them through the model just for shits and giggles. And if they happen to work, then that's a speed up. This is something that you can do pretty easily in a dynamic way. And actually, in vLLM, we hope to enable this by default if we can be really efficient with it. So, but currently, it's opt-in. So try it out. Another optimization is disaggregated prefill and decode. We talked about chunk prefill and trying to make prefills hurt your decodes less, but they still hurt your decodes. And frankly, they make your prefills slower as well. So when we're talking about high concurrency, high load systems, we need to start to consider actually physically separating our prefill versus our decode jobs. And so we don't run into these wasted times if we have separate runners for prefills and decodes, because they're just not interrupting each other. So, and to clarify, this means you have your requests coming in, you run those prefills on one GPU, and then once that gets finished prefilling, then you transfer those jobs to be scheduled on a separate set of GPUs that you have for decoding. And here's an example of showing that when you co-locate, when you use one GPU for prefill and decode, when you need to hit certain good puts, some latency targets, you're really limiting yourself in terms of the requests per second that you can process per your GPU. Obviously, you can scale this up. You can do 3 GPUs of the co-located, but you're going to be stuck at that 1.6 requests per second that you can serve from that GPU within your latency SLA. However, if you disaggregate and on paper it looks less efficient, you're using 3 GPUs, 2 for pre-filling and 1 for decode. However, you can serve more requests per GPU because you're specializing these GPUs and in order to better serve your latency metrics. So this is a really, really important optimization that we've started in vLLM. We have basic support for, but this is what's used for the really big, large production runners like OpenAI or Anthropic or Meta, to say the least. So that's most of what I'll talk to you about here. I'm happy to make you eat your greens here, but check out the docs on vLLM for some of the other methods that we and to learn how to actually use them in vLLM. What neural magic on quantization, inference, on the Torch compile integration, to try and reduce few just lowering system overhead in general. And of course, bringing all of these, production metrics, production features that we find when we bring enterprise customers to scale vLLM, and hopefully bringing that to all of you in open source. And rising tide lifts all boats. Also, we're a top contributor to vLLM. I am the top contributor in Neural Magic. And yeah, so we work on all things inference performance engineering. And if you're interested in that at all, we're hiring. Please, if you write CUDA, please join me. That's all.
Craft really want to, but some mic will bring you like. Yeah, so if you could go back to the disaggregated prefill slide. So you need relatively fast interconnect between the prefilling TPUs and the decoding TPUs because you have to migrate. You have to map the KV tags from the prefill onto the decode.
Yes. Yeah.
And roughly how many bytes per token? That's going to scale with model size, right? As well.
Yes. Yeah. It's bytes per token. I mean, it's on the order of a few megabytes. If I'm thinking right.
Per token. Yeah. For the 8 billion and 70 billion parameter models that people are.
Yes. Yeah. But the key thing is that I simplified it here. We're really considering single GPUs, but the key thing is that particularly for really long prefills, it takes a lot more time to do that prefill than to move the KV cache over decent interconnects.
Where decent is defined as InfiniBand or Rocky.
Yeah. Not NVLink, or not InfiniBand. I can show.
Okay, yeah. We can take it out.
Yeah, we can take it offline. But the key thing is that when you specialize sort of prefill and decode workers, you can actually set up different types of model worker configurations. Where, for instance, you really can scale up your tensor parallelism really, really hard when you have a lot of compute for running, really large prefills. Whereas you can't necessarily do tensor parallelism where this is basically where you're splitting up every layer and requiring synchronization on every layer. But this is the way that you scale to get
better compute on small decode batches. Just because if you're running a small decode batch, then you're going to run into the communication overheads, and that's really going to hurt you. Whereas if you're running a peaceful worker, you can really optimize for that and generally get your time to first token down if you can specialize in these ways. It's definitely a thing that can bite you in the butt, though. So it has to be built at scale.
Still, it seems like the Torch compile is a bottleneck, and we keep trying to optimize it and increase information back. The question to you is, for you guys considering using ML to essentially optimize compiler, like with things like reinforcement learning, looking at multiple examples. And the reason I say this is because there's a paper IBM research coming the point of failures where they improve the performance of compilers significantly by using it.
Yeah, I mean, I think it's really interesting. We certainly can't hire enough good people that can write GPU kernels. So, and we actually use Torch Compile not just for its automatic compilation, but for injecting sort of custom fusion passes. The great thing about Torch Compile is that it now gives us a graph we can compile, and we can go back to sort of traditional compiler basics versus needing to replace just one operation at a time. We can actually have a graph and perform passes and insert custom kernels, but we're limited on the number of custom kernels we can substitute in because you need to identify them and have the people resources to make those. But unfortunately, because we write so many kernels for everything else, like for our linear layers, for our attention, for our RMS norms, for our collective communication, for tensor parallelism, we already have so many custom kernels that to Torch Compile, they're binary blobs that they can't really do fusion with. So we've already done most of the easy fusion. So currently, it requires some of this sort of manual fusion work if you want to both have, optimal kernels and also optimize for small, do larger scope optimizations like that you could do Torch Compile.
And so I was curious, Red Hat require you best. So what side of that is like the security side, like data poisoning, or what types of the product line that you guys have been, making and merge together?
I'll be honest, I am not going to work on that. I'm going to keep working on vLLM, and most of us are going to keep working on vLLM. So, I mean, Red Hat already uses vLLM for a lot of their products and their offerings, and they just want to make that product. They want to continue to make that project better. So
that's complementary to you.
Yeah, I mean, we got acquired so we can keep working on vLLM.
Oh, interesting. That's good.
Yeah, so we're going to open source more kernels. That's the goal. Yeah.
What was her name?
You got Red Hat.
Thank you, Jesse.
Let's wait for the mic for the questions, please.